So then we hand over to Professor Anders Rantzer from Lund. He has actually 15 minutes, so you get 8 more minutes for an ERC grant.
Okay, very good. So thank you very much for this opportunity to address this audience. So I would like to tell you a little bit about our efforts to do theory for large-scale systems. So what is a good example to start with? I think the energy network is maybe the best example of a very large-scale system which has lots of control problems in it. And you could argue that, okay, we have had electricity for 100 years, and it seems to work. So why bother? But actually, it's increasingly hard to control the network when we are relying more and more on renewable resources like wind and solar, which are less predictable, and when we are taking out nuclear power stations in many places. But if you want to do mathematics and for the purpose of understanding what's going on, the power system, it's maybe not the best example because there are so many different models that are used to describe different aspects of the power network. So it basically has to do with what timescale you are interested in. You could address very short timescales, like what happens when there is a thunderstorm somewhere and giving a flash, or a much more slow scale. But so we try to look into something more focused and simplified. Here's another energy network which will be an inspiring application for our project. And this is the new generation of heating networks. That's something that's much simpler to model, but which is also has a lot of large-scale aspects that are relevant, and which also will be very important to do if we want to get cities that are heated without relying on oil and gas, and because then we are really needing these kind of heating networks on a more systematic setting. And if you do it with low temperatures, it's much cheaper to install it, but also harder to control. So that's another very good driving applications. Maybe even easier to conceptually consider is this kind of water channel system where you have a number of places where you could control the flow, and you want to do this in a way where you don't need to have a model of everything in order to the local control. So you would like to rely on local communication when needed, but certainly not on centralized information processing. Maybe irrigation systems are not the most frequent in Sweden, but there are some related ones. This is actually a schematic picture of Lule Älv. If you don't recognize it, it's because it has been adjusted a bit. So this is some additional curvature. You start here up in the Swedish mountains, and then eventually you end up in Boden. But there are a few places where you have hydropower stations, like in Laxede, and another one in Vittjärv, and in those places you can control the flow, and then there are a number of places where you also can measure, and this is an old picture. These controlling the water flow in a Swedish river is important nowadays when you want to use those rivers for storage of energy. So if you have solar and wind, which is not so reliable, you could use hydropower to even out and store power until it's needed. On the other hand, this has some environmental impact. So fishes and birds and so they don't really like water going up and down all the time. So there are very conflicting objectives, but it is yet another example of what I would just put under the headline of buffer networks. So you have a number of buffers, you have some connections, and you have some producers, you have some consumers, you have some storages. And we would like to have some good theoretical support for control of such buffer networks. And it could be water, it could be power, it could even be traffic on the roads or data networks. But there are joint features, and there are also features that are, of course, very different. But it's a good theoretical challenge to try to get some theory that can support the basic framework for such buffer networks. And there could also be single commodities or multiple commodities. There could be interaction with humans that are more or less important, like in the those district heating networks. It's very relevant to also model human behavior so that you can control the network and only heat where it's really needed. So what do we need for this? So we're speaking about a scalable a theory to support scalable control, but there are many aspects to this. We want synthesis methods that can allow us to design these feedback loops that are needed. Usually that's done with very simplified models, but then more advanced and more accurate models are used in a verification phase. And also that has to be done in a scalable way. Then we have the modeling issue. For a very large-scale system, there are always things that are changing, and it could be very expensive to keep the models up to date. So ideally, we want to do that in an automatic way using learning techniques. And we also need to learn objectives, actually. What does the user appreciate, and what does the human in the loop really want out of the system? And this can be conflicting objectives that need to be coordinated. So we will now focus on a very simple aspect, because I plan to give you some idea of what theory that could be involved. So this is a very simple model of 3 water dams, and you see that it's a discrete time model, and here, these numbers in this first and second column, they sum up to 1, which indicates that some water stays in the first dam, while the rest of the water goes on to the second dam. And the same thing happens over here. 80% stays and 20% proceeds if no control action is going on. Then you have the control action here, which can adjust how much stays and what goes on to the next level in the river. So now we would like to have a scalable control law, which means that we want to take the measurements here and we want to map those measurements into control action, but we want to do it in a way that can scale up to tens of thousands of buffers rather than just 3, which typically mean we would like to have local information used for the decision, not knowledge about everything. So there has been quite some work done on this over the past 15 years or so, but most of it has been focused on sparsity in transfer functions or input-output maps. And here you see that with this model you will get a triangular structure because the input that you U3 will not have any impact on the first and second dam, so because it's further down the river. But when you do control action at the first dam, it has effects on everything. And so you get a triangular transfer matrix. But already here you see you lost a little bit of information because originally we had a 0 here saying that the influence from the first on the third dam only is indirect. It has to go through the second, and this is not really visible in this picture. So we are arguing that there is a better way. There is another, maybe more severe objection to these transfer matrix sparsity methods, that for many sparsity patterns, you would lose them if you invert the matrix. But here's another one. You can look at an arbitrary graph with vertices and edges, and then consider state realizations, A, B, C, D, of a transfer matrix. And if A and C are 0 wherever there is no edge in the graph, then you say that this transfer matrix is network realizable according to this graph. And this is a better concept because it turns out if you add or multiply 2 of these matrices, it will remain network realizable. And you can even invert the matrix, and it will still have still remain network realizable. If you want to check that, you look at the the state realization of the inverse, and you see that if A and C are sparse and B and D are diagonal, this will still be okay. So I'll skip that. But now, so now we have this concept of network realizability, and we can actually optimize. We can optimize matrices using convex optimization because it's a convex set. We can use convex optimization to find such a matrix which gives a good map from, let's say, references to inputs or references to outputs. And then the next step is to actually implement the controller, and then we can use this idea of internal model control, where you just keep an internal model which tells you what was expected, and you compare it to your measure, and only when there is a difference you make some adjustment. And the nice thing about this way of implementing is that it can be completely distributed. So let's look again at this river dam model. It's consists of banded matrices, and now I use convex optimization to find a queue which has the same banded structure. Now I can implement this on my river. So in the first dam, I keep a state estimate for only the local state, and also the corresponding part of the Q matrix. And that's done for every location along the river. And then you see that the total controller gets the same banded structure. You get a few things that are updated locally, and you forward information downstream the same way as the original river model. And in this way, it becomes completely scalable. It doesn't really matter if it's 3 or 10,000 different dams along this river. The local information propagation will still be the same. And of course, this still relies on local knowledge of some model parameters, but you can imagine doing local learning. So in this third dam, you use some learning or adaptation techniques to estimate, but you only need to estimate the local parameters because the other parameters are not relevant. So in this way, you can also do distributed learning for the purpose of the control of these dams. Okay, so To summarize, that we want to move away from sparsity of transfer matrices. It's not the right concept because it doesn't have the right algebraic properties. If you, especially if you do inversion of a sparse matrix, you destroy the sparsity pattern. But with these network realizable models, that's no longer the case. So that's the right concept, we claim. And you can use convex optimization. Even those convex optimization algorithms can be run in a distributed way to find all the relevant parts of the realization you're looking for. And then eventually you can make a scalable implementation using this simple idea of internal model control, where everything is localized in the network. So I just want to thank some of our collaborators on this, and I look forward to having more people involved in the next few months. So thank you very much.
So now we have time for some questions. Anders?
So can you also design observers for this so that you can speed up the load disturbance rejection?
Yes, that's a natural part of the concept because this internal model is essentially can be viewed as an observer. And
Can you speed it up?
Speed up.
Yeah, the open loop dynamics, so that you get faster observer than open loop model.
Yes, you can definitely get the closed loop system to become faster than the. That's the idea of most of control, that you speed up the performance of the system, right?
With that controller?
With this type of controller too, yes. And if you want to deal with unstable systems, then it's a bit more complicated. But for stable systems, you can do this. Yes.
Yeah. Great idea. I think you may need some assumption about cycles or the absence of cycles. What precisely?
In general, this works also for systems with cycles. That's the difference between the. You saw with the transfer matrix that if it's lower triangular, then if you invert it, it remains lower triangular. If you want to preserve sparsity patterns under inversion of matrices, then you need some kind of tree structure and avoid cycles. But the point here is that this does not require the absence of cycles in the same way.
Last question. Last question.
So when you're talking about the distributed implementation of the convex optimization,
yes,
have you thought about what exact distributed optimization algorithm you're going to use, or what distributed architecture? And is that going to take advantage of what he asked, like your banded structure and sparsity pattern?
And there is a lot of work done on how to do optimization over transfer matrices like this. It's basically an infinite dimensional convex optimization problem. So usually the way to do it is to make it finite dimensional by using some basis functions. And the choice of those basis functions will have an impact on the algorithms, but also there is a lot of work done on distributed optimization, which I'm I'm not really the expert on. Mikael Johansson has been working much more on that.
Just a quick follow-up. Can you point me to some reference material on that?
Yeah, I'd be happy
Maybe
to.
later
Please
on.
send me an email and I'll
Sure.
do that.
Thank you very much.
Okay, then we thank Anders once more.